It's my great pleasure to introduce Dr. Lara Martin, who recently finished her PhD at Georgia Tech and is the first author of one of the papers that we read 2 sessions ago on deep learning for event-based story generation. She's now a postdoctoral scholar at the University of Pennsylvania. And thank you so much for being here, Lara. Take it away.
Yeah, thanks. This presentation is actually, it's basically my defense. So I'm just gonna, it's gonna be like a faster and slower than it would have been in the original presentation. And please feel free to stop me at any point if you have questions or you just want to talk about something. All right. Yeah, I'm going to talk about neurosymbolic automated story generation. So I'm actually going to skip this first part because I'm sure that you're all very familiar with storytelling and why it's important. And also the way automated story generation is. So. But I'm going to actually go into this a little bit because there are a couple of points that I want to touch on that fit into the rest of the talk. So the system on the right might look very familiar to you. It's actually created by Dr. Ware. So so the systems like these are they're very easy to understand, and they have they're very logical the way that they flow. So like one of the first systems, Jin's Tailspin in 1977, it has the story about Joe being thirsty and wanting to not be thirsty, and so he decided to be near the water to solve his thirst problem. And then in 2014, the CPOCL planning algorithm creates more complicated and interesting stories, but it's still left in a constrained world. And so there are a couple things that I think are very useful in these symbolic systems, like classic AI, that like schemas, causality, and planning, and I'll go through each of these in order. So symbolic systems like this, so say we have like a very simple chain, like standing in line to pick up drugs at the pharmacy, and hopefully at the end of the story, the customer leaves with some drugs. And so in this, you have these nodes where you can have something like pharmacist asks for prescription, and this is known as a schema, and this is just a way of symbolically annotating these events. You can also zoom in on a link and see, okay, well, in order for the customer to, in order for this chain to continue, the customer needs to have the prescription in order to produce it. So when the pharmacist asks for prescription, it's basically the system asking, and then you need the prescription in order to continue on. And you can continue, you can have longer term causal links called causal chains. So in order for the customer to leave with the drugs, the pharmacist needs to deliver the drugs. And in order for the pharmacist to deliver the drugs, the customer has had to produce the prescription. And hopefully these systems are a little more interesting and they branch. And so maybe instead of the customer always producing the prescription, maybe they don't produce the prescription, and in which case the pharmacist has to call the doctor and stuff. And so this branching leads to planning, meaning that the system has to try to figure out how to reach a goal. So there are pros and cons of these models. They're really coherent, but but they require a lot of knowledge engineering. So there's possibly lacking in diversity and novelty, which means that there's a limited domain. So in comparison, I would like to create stories that are open world. So where the set of all possible events that can occur in a story is the same as the set of all possible thoughts that a human can think of and express through language. Or in other words, this looks like I have a story prompt, so the first sentence of the story, and I talk to my favorite voice agent, and it tells me the rest of the story about anything. And the way people have done this, including myself, is by taking a ton of stories and feeding them through a neural network to train it, and then hopefully at the end you get a story. But what this ends up kind of looking like is, so sequence-to-sequence neural networks, I trained this on a bunch of movie plot summaries. And so like if I have this sentence, R2-D2 carrying some drinks on a tray strapped to his back passes Yoda, who uses his force powers to hog the drinks, what I expect and what is actually the next sentence in the summary was Obi-Wan and Anakin are drinking happily when Chewbacca takes a Polaroid picture of Anakin and Obi-Wan. But what I get instead is Chemist Block gives him the advantage to personally run around with a large stick of cheese. Which is really interesting, but it doesn't make any sense at all. It's not relevant. To compare these two types of systems, symbolic systems are really coherent, but they have limited domain, whereas neural systems can create these open world stories, but the coherence is terrible. And I don't think I have a slide in here actually, but you might be saying like, well, these, you might be comparing the sequence to like GPT, and while GPT does create more fluent text, it still loses coherence over time. So actually I do have, I don't know, I'm getting confused between this talk and another one. Anyway, so wouldn't it be great if we could have stories that are both coherent and open world?
This is great. So, you're really tying together like basically all the major high-level discussions we've had throughout the class. So this was a really perfect guest talk to sort of conclude the semester on.
I'm glad. Yeah, this has come about through my frustration of working with both ends of the spectrum and seeing like, well, why can't we just do both? Like, and so I tried to find ways to try to combine the two. So in my thesis statement during my PhD, I looked at including these symbolic approaches into neural systems. So these schemas, planning, and causality in particular, which I call events, plot progression, and reasoning. So back to this example about running around with a large stick of cheese, you might be wondering, well, what? Okay, so here's the, see, it's been a while since I've given my defense. So yeah, so yes, here's my GPT example. This is when I actually ran it through Talk to Transformer. And this was the first time I actually played with it, and this was the first sentence I put in was, the hungry dog licked her lips as she watched her owner eat. And then I get this really interesting story, but as you can see, it kind of like drifts off topic a little bit and loses track. So it goes, she could see the white teeth in his jaw, then moving behind his right ear. So immediately it's switching the gender of the dog. And then it says, the hunter picked up his sword, directing the dogs in a cloud of mutterings. Did you just feed a dog? She demanded, suddenly even more agitated than before. Yes. Jack's voice was rough, and he hated that word. His face was tight and angry. She has killed something important to us, and now the house is filled with blood. It makes me sad. She is one of the most dangerous wolves I've ever met, and if she bites me, she will lose. John shrugged. Well, it's not your fault, he said. So there's this introduction of these characters of Jack and John, which is normally kind of fine, but like as these systems go on, they keep on introducing these characters and then they just forget about them. This dog becomes a wolf at some point, and there's the owner is no longer mentioned, and instead is this hunter, and it's very Call of the Wild all of a sudden. So yeah, it still loses coherence. And the reason why, or one of the reasons why this is happening, is because there's sparsity in these data sets. So when you're training these models on these stories, like you only see these stories once in the entire data set, or like you only see a sentence once. And so, but normally this is a good thing because like authors like to be unique when they write stories, but it's not great when you're training a neural network. So the way that I approached it was by separating semantics, the meaning, from the syntax, the grammar, using these event representations that you were supposed to read about. But this actually creates more overlap in the data. So you will see these events occur more than once, and then hopefully the network can pick up on these patterns. So the event representation that I initially used was this subject, verb, direct object, and a modifier. Later on, I added in a preposition, which is kind of a callback to the original Pachota and Mooney that I based it off of. But I also took this, so like, say I have a sentence, Yoda uses the Force to take apart the platform. I extract the event, Yoda use Force empty parameter. And I took this a step further by generalizing the event. So Yoda is, I did named entity recognition, Yoda becomes person 0, and I looked the verbs up in Verbnet, which is like a data set that buckets verbs by their semantics. And I looked the nouns up in WordNet, which is a hierarchical dictionary. And I went up a couple of levels in the hierarchy to get like a more general category. So force becomes power. And I called this system Aster, which I thought was very clever because it's also a pretty flower, but it stands for Automated Storytelling with Event Representations. And the way that it worked is I would eventify a sentence, so John unwittingly unleashes an insidious pox, which I apologize for. I've been using this example for a while now. It was pre-pandemic. And the event I would get out would be like John unleash pox, empty parameter, or the generalized form would be person 0 disassemble contagious disease, empty parameter. And then I trained a sequence-to-sequence neural network to generate the next event in the story, male spatial configuration, empty parameter, adopt. And then I could just like loop through this to create a longer and longer story. And then I saw that by generalizing these, well, by creating the events first and then generalizing them, I was able to lower the perplexity. And perplexity is a measure of how surprised a model is by new like testing data that you give it. And so lower is better. And then but once I have these events, they're not really readable. So I created another network, event to sentence, where I just translated these events into English sentences. But I decided to keep them generalized because that actually adds in a pretty useful like component to the story generation pipeline, because like my example that I give is, say you have a whole corpus of cat stories that you trained your network on, and but now you're telling a story about a dog. Well, because the system, because these events are generalized, and it sees carnivore, it's able to fit dog into carnivore because you were talking about dogs in a specific story. So even though it was trained on these other carnivore stories, it can adapt. So with the, and it also saw that the generalized stories, sentences, tended to do better when I was translating them back into sentences anyway. And here I also looked at BLEU scores, which is often used in machine translation. So translating from one language to another normally, but here I was translating from events to sentences. And so as the story would go on, it would remember these tags and what they were referred to, so it could plug them back in using this sloth feller. And you would get something like, he crumbles and is about to be husked. So for the rest of the talk, I'm going to focus in on this event-to-event loop, and I'll look different. I looked at it a couple different ways. So far, like, writers like to be unique with their writings. This makes it hard for machine learning to see these patterns. So I created a schema to aid the pattern matching, but this creates a system that still likes to ramble. So the way I got around this rambling was through plot progression. Because oftentimes, or in most stories, I would say, there you have a bunch of major plot points that you have the story or the characters kind of go through. So say you have a romance story where you want the characters to meet, and then there's unrequited love, but then they admire each other, but then there's a terrible discovery, but they have an understanding, and then they get married at the end. So how can we get a neural network to reach one of these plot points? So the way I did it was by taking my event-to-event the sequence-to-sequence network, and I used an algorithm called reinforce, which is kind of like reinforcement learning, but without states. And so what it was doing was I would see, okay, is the network heading towards this goal? And depending on whether or not it was heading towards the goal, I would give it a reward signal, and I would backpropagate this, and it would retrain the model.
Could I ask a question?
Yeah, absolutely.
How did you determine whether output was heading towards a goal?
Yeah.
Like what metric was used to decide?
So actually that's the next slide. So what I was looking at is, it was a two-part equation. So the first part was, how close is so going back to the events, I decided to just focus on the verbs. And so say we have, our goal verb is to marry. So I looked at, in the data set, how far away is this current verb from our goal verb, and then so I would get, the closer the distance, the higher the reward. And then the second part would be based on how frequently this verb occurs at any like distance from the goal verb in our existing stories. So I would have if it appears frequently before the goal, I would get a higher reward. And so multiplied these together, and then what the secret sauce is that I ended up creating clusters based on this score. And then I would constrain the system when I was training it from only sampling from the next cluster. And so this created like a artificial state representation, and it prevented the system from just like being like Joan and Bill meet, they get married, which it would often do when we were training without this clustering, because it wanted to get to the high reward, it wanted to get to the goal. So, and by not having that state restriction, it was able to just jump to the end. So this enabled it to not only achieve the goal more frequently, but it actually lowered the complexity as well, which is interesting because it's kind of saying that by doing this clustering, we are able to like capture something from the original data set that we couldn't do by just doing like regular loss functions. Yeah. Do you have any other questions? I guess I should have stopped after the first section. Sorry.
Oh no, I have a bunch of questions, but I will save them for the end and try to not take up all the time.
All right. Yeah, I don't know how. I'll try to speed through some of this so I can get to the third part, because I think that's pretty cool stuff. So yeah, so to summarize this, I ended up doing a human subject study, and people agreed that by having this reinforced algorithm to guide the network, that people thought they were more coherent stories. Yeah, so I was able to fine-tune this event generator to behave like reinforcement learning and create artificial states. And while this made for consistent plot-driven storytelling, it's still not causally coherent because it's still relying on this probability. So here's an example of the types of stories that came out of the system. So even though it reaches the goal of hate/admire, it's kind of just jumping to the end and doesn't completely make sense. So it goes, our sister died, Gregory executed during the visit, Gregory adopted the girl looked like her mom, she was appalled, Penelope detested the jungle gym. So how do we get to make these stories more causally consistent? So the way that I did it was by using Verbnet. So the way that Verbnet works is that it has a bunch of different components. So if I have a sentence, Jen sent the book to Remy from Atlanta, I get things like the roles were the agent, Jen was the agent, the book was the theme, Remy was the destination, and the initial location was Atlanta. And then I get these semantic predicates, like at the beginning, the book has location Atlanta, and then all this stuff happens, and at the end, the book does not have location Atlanta, and the book has location Remy. And I also get information like the agent has to be animate or an organization, theme has to be concrete, initial location has to be location. And these are called selection restrictions. I would sort these into pre and post conditions. And then I use this in conjunction with the event-to-event network. So I took the event-to-event and I had it produce my candidate events, so it was just running like normally. And then I ran it through my Verbnet world engine to create a story state. So it'd be like, okay, well, right now Remy has possession of the book and is animate, and the book has location Remy and is concrete. And then this prunes out events that are not consistent with the story. I randomly, at the moment, select events, and then I get much better stories. So here's an example of some longer stories that I actually hand translated from events, where, as you can see with the neurosymbolic system, it brings back these entities, and it doesn't just kind of like become a stream of consciousness like a neural network normally likes to be. So like with the pure neural system, it just like completely forgot about the traveler immediately, and it didn't bring them back. Whereas with the neurosymbolic system, they come back after a bit of time. And I can wait here for a few seconds if people want to read these.
Who was Kevin? Was that the goal? Did you provide the beginning and the end, and it had to?
No. Yeah, sorry. With this system, it actually we didn't do the deep reinforcement learning stuff here for the causally consistent stuff. So this was just a regular like event to event model.
But so what if any input does the system take? Like, did you give it the first sentence, or did it just
the first sentence?
Okay.
Oh yeah, so these were actually events. So I actually gave it the first event, and then it just produced a bunch of events. And I did all the. I also have stories actually in my thesis if you want to read them. I put them in the appendix. Where the whole system, like the full system, created the story. But here for a little bit better readability, I hand translated them. But it's because of this readability issue is why I actually switched to GPT instead of events. But I still tried this causal, this like causally consistent rule engine, and that worked well with GPT as well. So I think I have an example of that next. So now I'm talking about, you don't need to know about this. This is boring baseline stuff. But but basically, there's this adding symbolicness made it seem more like a single plot and had more of a plausible ordering, which makes sense. And the neurosymbolic system had avoided more repetition than the neural system. I could talk more about this symbolic only system if you're really curious, but I'm going to skip it for now.
I am a little, could you just give us a 1-second version? Like when you said that, I was expecting it to be like a planner or something.
No, it's actually based off of Verbnet. So with Verbnet, you get, it has these frames, and in these frames it gives you a syntactic construction. And I used that to kind of generate these sentences, and the way that I selected them, instead of like pulling from a distribution, I pulled from like a I just pulled from a I did pull from a distribution, but it was just me doing like a frequency analysis of the data set. so it wasn't like learning anything smart about it. So it kind of, yeah, I was a little surprised and like, why is this really stupid system doing so well at creating like stories that are perceived as a single plot? But I think it's also because of this improved readability that having Verbnet provide this syntax helped go from like create sentences instead of going from events to sentences. Yeah, so I also tried it with transformers. I used fine-tuned GPT too, and so instead of using events first, I actually kind of parsed it after the sentence was selected, kind of created like an event representation then, so it would fit into my Verbnet engine. And then I did the same thing. And so what's nice about this is that it kind of simplifies the whole pipeline and gets rid of that extra neural network. So here's an example of the transformer-based system. Christopher attacks Harriet. The king tries to take him away. Christopher is taken away, but is quickly saved by Aigner. The king is able to escape the tower. Christopher and Christopher are able to get Christopher out of the tower, where the tower is still on the king. Penelope and the king are able to save Christopher. So I really like this story because it, except for this sentence, it makes a lot of sense. It's doing, I think, really well. But I also like the sentence because it shows the weaknesses of the system and how it's still, like, if the grammar for that GPT like has, like, produces, it just completely throws off the system. And so like, it shows that even though I tried to be thorough with this, there's still stuff that can fall through. But sometimes that can make things really interesting. So when I compared these systems, the regular GPT to my neurosymbolic system, it did a lot better with plausible ordering, making sense, and being received as a single plot. So that's really, really promising, I think. Really cool. And then I also compared it to...
Is this a 5-point Likert scale that you're working on?
Yes.
So is 3 neutral?
Yes.
Okay.
Yeah. So as you can see, like people don't like these stories. they're not great, but it's statistically significantly better than the if you just did things with a neural network.
Absolutely, yeah.
Yeah, and yeah. So I also looked at how it behaved, like, with the 3 systems, so with the symbolic only system, compare it against these, because of that weird single plot thing. But it seems like they're not really statistically significant anymore. And that shows that by having this transformer produce the sentences now, we're no longer having that Verbnet advantage. And in fact, like, you could see with correct grammar that it actually, both of the GPT versions are performing better than the symbolic. And so this is what Tucker said about the symbolic only system. while difficult for me to understand, the story does seem to follow in plausible order. And so that's promising, and it shows that these symbolic systems, well, I mean, although my symbolic system was weird, so it made it more difficult to understand, that even though it's kind of creating this stuff randomly, by doing this pruning, it still creates a plausible order. So to recap, in total, storytelling systems are important. By separating the semantics and syntax, we're able to generate, have language generation that can be longer and can concentrate on the meaning throughout. And it can have controllability of these systems, so it has an ability to solve long-term plans, which is also coherence. And by creating these causal systems for reasoning and maintaining state, it has these generative systems that are consistent. So that's thesis statement. So in all, making sense is most important, because this does not make any sense. I have nothing more to say here. Have your next story make sense. So frustrated Turker created a call to arms for story generation. All right, that's it. Thank you. Do you have any questions?
That was amazing. Thank you. It's cool to know about. I hadn't known about this more recent, more symbolic work, so that's really neat. I was familiar with the 2018 paper.
Yeah,
It's really cool.
It was a lot of stuff happened, and it was hard to publish on, not because of my own stuff going on. So
finishing a PhD.
Yeah, basically. But it's in the thesis, and I am currently trying to finish up a paper to at least put on archive, and then put in an actual conference somewhere.
Cool. So we've got a little bit of time for questions, so I'm just going to open it up to anyone. Sometimes people need a minute to sort of think about questions, so I just wanted to jump in with one. And I guess this is more of a request to speculate about future work. So I like that you're sort of going more and more towards this some kind of logical model of the world and of the current state. And less, letting the neural net kind of handle that as a black box and more modeling it explicitly. And I always wondered, I guess partly, I always felt like these systems were not really saving a lot of effort on knowledge engineering. It's changing the nature of the knowledge engineering, because now you can get stuff from Wikipedia, but there's still a lot of work that goes into collecting that data set and cleaning it and parsing it, and then not to mention all the work that went into the authors of the Wikipedia articles to write it in the first place. So I always wondered if you could use something like GPT-3 or one of these systems to build a planning domain. I love working with, these sort of more formally symbolic systems like the planning systems. But as you say, it's very reliant on one human author sitting down and writing it and doing it correctly and debugging it, and then how do you add content? And I always wondered if you could do that, take it even one step further in the direction you've already been going, which is use an actual formal planning model, but write the domain decide what actions and then figure out what the preconditions and effects of the actions are using this machine learning model and or Verbnet. Because you were sort of doing that already. You kind of had that, you were sort of had that preconditions and effects thing going on. Yeah,
the only thing that's missing is the actual planning, or the selection of a smarter selection of the events. Is that where you're kind of going?
Yeah, well, and I mean, I guess I was going more towards, could you make a planning domain suitable to hand off to a planner or to some other kind of system that you got from this, Wikipedia? Are you using the Wikipedia plot summary corpus here?
Actually, no, I switched Corpora because I think it was too diverse and the stories were too inconsistent in length. So I actually created a new corpus that if you're ever interested in using. It's a science fiction plot summary. So like a corpus. So it's like Mark and I figured that sci-fi nerds are probably really thorough in their descriptions of like these long-running TV shows and their episodes. So I just like scraped a whole bunch of wiki. So yeah, again, it's wiki plot summaries, but it's more by fans of the shows and less of like this kind of general audience, I guess. And so I actually get some really long stories from this, which is pretty cool. And I get to see like how, I think it'd be useful to see how characters evolve over time and do things like that. But back to your question. So you were saying, yeah, how can I use a neural network to like bootstrap a plan, like a pure planning system? Yeah, I'm actually, so I will say that I haven't actually built like a pure planning system, so I'm not completely familiar with that process.
And I know that's not necessarily your interest or your intended future work, but I'm just more like, I see something like this happening. I said like, ooh, I wonder if I could use that.
Right. Yeah, no, I think it could be so in my system, I'm using the neural network to generate the next sentence, and you can I could see you could probably use it to there could be a couple of different directions that this could go. Like if you want to have
something I'd kind of just the very after 1 second of thought, the way I would try to engineer this first round would be like, there's a rob action, like person 1 robs person 2. And then I wonder if you could just collect preconditions and effects and all that by prompting GPT-3 or something and say like, in order to rob person 2, does person 1 need to be alive? Yes or no? Like in order for person 1 to rob person 2, does person 1 need to be holding an item or need to be holding a weapon or something? And I mean, does that make sense? Like this sort of like prompt engineering to build a truly symbolic system?
There's it's not quite a symbolic system, but there's someone else working in Mark's lab who's currently doing kind of backward story generation. So it's like, this happened, why? Or how did that happen? And it kind of, and it's using backwards Comet. So I don't know if you're familiar with the tool Comet. It's actually something that I'm currently working with as well, where it's like a common sense system, and given a sentence, it gives you like possible like how did this person feel when that happened, or what did they do next, or what did they have to have in order to do this. So all these things that it's generating, and Louis Castricato, the guy in Mark's lab, reversed the model, and so he can kind of ask it like, okay, well, if I have this, what's the sentence that I get? So it's kind of almost exactly what you're describing.
Cool.
Minus the planning aspect as much.
Yeah, sure. That's right.
But yeah, there's I think a bunch of different directions that this can go in. Currently I'm working on like looking at more of a character-based generation, because I focus so much on just like a general plot that I'm trying to see, like, can I predict how someone's going to act in a certain scenario?
Oh, I like that. Yeah.
Yeah.
Okay. What about our other audience members? Mira, I know you're doing some work now on deep learning for story generation.
Right. So I had one semi-technical question. So where you're generating events and then pruning that with Verbnet and saying, is it actually possible to take this event, right?
Yeah.
So do you just generate a batch and prune out the ones that can't really be done and keep doing that until you get one, or?
Yeah, that's the way I'm doing it now. Is I kind of like figured out a pretty good number to always pull, like, so I'm always getting like 15 events or so, and with that number I usually get at least a handful of ones that are working. And so yeah, it's not an exact process, but
yeah. So if it might be an edge case, but if the system does not feed you any events that are reasonable to do you do anything in particular, or you just?
I think I haven't really. I think I just resample, or I just like, throw out that story. I haven't really put it in like an interactive system or anything. So I've just been looking at like what are the stories that I can generate, and if it just stops, then I just stop it. So actually, what I was originally planning on doing, like Stephen kind of was assuming, was that I was combining the reinforcement learning stuff with the causal stuff, and that's what the direction I was doing first, but I realized that it was way more complicated than I expected. But I've been working with someone who has been, I think he finally had a breakthrough, and so we're having the system like plan towards a goal and also be causally consistent. And so when it runs out of options, it just kind of, I think it just kind of fizzles out. It's like, that's not like it's learning that that's not the path it should take, kind of.
Right. And one more question on just how the Verbnet fits in. If you see, get something from Verbnet and you find this has preconditions that are, these haven't been established, these are just totally new symbols, do you just kind of go with if it hasn't been said that it's not true, it's might as well be true?
Right, yeah. So yeah, I've kind of gone with like an open world idea of that, yeah, as long as it's not explicitly contradicted, I'll just accept it.
Right. Okay.
Yeah. Thanks.
Other questions?
Sorry, I didn't quite answer your question, Stephen. I need to sit down and think about that one more.
That was a great answer. I mean, these are just conversations. It's all just about speculation and where to go from here. I love your work for many reasons. One of them is that I see the cross-pollination of so many different storytelling theories. Like, I see obviously the influences of the planning stuff that I do, but like the deep learning stuff and even like some earlier like Tailspin universe style systems all showing up in one way or the other. Mm-hmm. Like, you're really sort of taking all the best parts of a lot of different systems in a cool way. And as you say, like there's plenty of, ground left to cover, but it's just so exciting to see all those things coming together in one system.
Oh, thank you so much. That's so sweet.
Well, thank you so much, Laura. I really appreciate you coming. And
Yeah.
thanks for writing that great paper that we got to read. And
Yeah,
good
you're
luck
welcome.
with
And
your postdoc and future career.
thank you. And I will say, if anyone wants to reach out to me, my email address is laramar@seas.upenn.edu. So, or you can follow me on Twitter. I have mostly been just reposting things, so I'm not too interesting lately. But but yeah, feel free to reach out to me. Oh, here's my website too. Yeah, so Langtech Lara on Twitter and laramartin.net on the interwebs.
Thank you so much, Laura. I really appreciate it.
Yeah, thank you for thinking of me.